Hello everybody and welcome back to Calc 3 Online. So in the last video we talked about the quadratic surfaces. Today I want to talk about the hyperbolic surfaces. So the idea with these is basically somewhere there's going to be a negative. And if there's going to be a negative between the squared terms somewhere, then you're going to get a hyperbolic surface. Just like that's the way you get a hyperbola with conic sections when you learn those. And the idea, again, is to mostly just kind of familiarize yourself with recognizing when you're going to get a certain surface. The question of making me have you graph like really complicated surfaces like perfectly by hand is not fair at all in my mind, so I'm not going to be making you do that. I really just want to make sure that you kind of see some of the similarities between conic sections and these surfaces. So I'm still going to use traces to kind of help you see some of these. This one is, I'm not going to actually say the name yet, actually. I want to show you the traces first, and then we'll talk about what that surface is. So in the ZY plane, we would want to let X be a constant to do the trace. So like let's let like X equal 0. If you let X be 0, you're just going to get Z equals Y squared, right? So you get a parabola just like that. If you let maybe X equal 1, then you get Z equals Y squared minus 1. So you get this, right? If you do 2 or something else, I think you can kind of get the idea. You would get Y squared minus 4, right? And so you're going to get, I don't know, something down there. But basically you would just get parabolas that actually can't be up here because when you subtract that term, it's going to be always a positive term. So it's always going to be shoved down. But you're basically going to get parabolas going down the z-axis like that. And if you do the xz plane, you want to let y be the constants. So let's do y equals 0. In this case, you get I guess I should write it, z equals negative x squared. So you get that just upside down parabola. If you do y equals 1, then you're going to get z equals negative x squared plus 1. And so it's just that previous graph shifted up 1. And you could keep doing this. You'll just get like upside down parabolas that move up the z-axis, okay? And one of the weirder ones is in the yx plane. So here, if you let, say, z equals 0, then you're going to get x squared equals y squared. And we saw before, that is actually just a literal graph of an x. And it just really comes out of, again, that you have x, this boils down to plus or minus y, and it comes out of like absolute value and how you solve, what happens when you take the square root of x squared, you get the absolute value of x, basically. So we get an x, which is kind of weird. If you let, let's say, let z equal 1, I think I'm going to do this down here, then you would get just 1 equals y squared minus x squared. And since the y squared is positive, then x squared is negative. That means it's going to be one of your hyperbolas that open kind of vertically here in the y direction. So you're going to get a hyperbola like that. What's another weird one? Let's do z equals negative 1. So if we do z equals negative 1, we're going to get, down here, we're going to get negative 1 equals y squared minus x squared. And that's just equivalent to 1 equals x squared minus y squared, which is a hyperbola shooting off in this direction, like in the x direction. And if you kept trying some more, you would see that actually you kind of you could sort of fill in all these quadrants that sort of get formed by the x. You can get hyperbolas all in here and here, you can get hyperbolas here and here. So kind of when you look at it top down, you're just getting hyperbolas in the two x and y directions. But if you look at it from the sides and you look at like the zy plane or the zx plane, you get parabolas, but they point off in different directions. So I'm going to try to draw it, but basically what you're going to get is so this is our x, y, z. So in the zy plane, you're getting like a parabola. And then in the xz plane, you get an upside down parabola. So it sort of turns like that. And so this is back here. But then when you look at it top down, it looks like a hyperbola in the two different directions. And so what this kind of becomes is something sort of like this. It's not perfect, but basically what I'm trying to draw here is actually what we call a saddle surface. And it literally looks like a saddle. All right, you probably heard that. Sorry, I got a phone call. But I think I was basically done saying what I wanted to say. So this thing really is a saddle. It literally looks like a horse saddle or something. And again, you should go and try these things in that Math 3D program. If you type in z equals y squared minus x squared, you'll see a nicely printed saddle, basically. Yeah. All right. So another one here. This time, you've got all sorts of squared things, and one of them is negative. And so before, again, it was just two squared terms, and the way that this z is the one that's not squared, that's actually why we get this saddle. If you made the y not squared, but the other ones were, then you sort of get this object oriented in the y direction. It would be the saddle is upright in the y direction. But here we're going to get something totally different because they're all squared. All right, so if I do in the zy plane, if I start off and just let x equals 0, then you're actually just going to get this right here, right? And that right there is a hyperbola. So you're going to get a hyperbola that opens up in the y direction. If you do, say, I'll do blue, x equals 2, then what happens is you get a 1 on both sides, right? Because you're going to get 4 over 4 on the left. And so then they cancel out and you get y squared minus z squared over 4 equals 0. So then it's one of these things where you get y squared equals z squared over 4. And this will give you that kind of x structure again, which really kind of acts as a asymptote for the hyperbolas, is really what's happening there. And I think that should be enough to see what's happening there. If you do y equals 0 in the zx plane, then you can see that you would get a hyperbola here. If you do y equals 1, you'll get here you'll get x squared equals z squared, which gives you, again, that weird x graph. And let's say in the last one here, if I do z equals 0, then I get x squared over 4 plus y squared equals 1, right? Which is an ellipse, and it's an ellipse specifically that opens, it's actually pretty easy to draw, so I can 2, -2, and then actually I should also add that this would be -1, and this would be 1, and that's just because there's like a 1 down here, so we're going to be going up to 1 and down to -1, but we get that ellipse. And if you do different z values, then basically you're always going to get some sort of ellipse structure. You will always actually have ellipses that move more in the x direction. So you get like maybe another one. So what you're getting is you're getting something that, and I'll try and draw it, but you're getting something that's ellipsoid, like here, when you look down it. And there's like different size ellipsoids like that. But then when you look at it from the sides, you get a hyperbolic structure. So that would kind of be like one of the sides, and then maybe here, and then in the back, kind of like that. But if you can kind of see what I'm trying to draw, you basically are getting what kind of looks like I'm thinking like a nuclear power plant reactor. So here's my nuclear power plant smoke, because that's not really a thing. But so you get like this kind of cone-like structure, but it's actually called in this case, because it's got an ellipsoid, when you look down it would actually be called we're going to run out of room, but a hyperbolic ellipsoid. Okay. So really just think like a nuclear power plant reactor. That's actually the exact shape of them. All right. So last but not least, this one is actually technically looks like this, and it's kind of got a weird name, and I'll write it down here in a second. But there is a big difference between this and the last one, and it's hard to see at first. So what I'm going to do first is I'm going to set this surface equal to 1, and something weird is going to happen. All right, so I'm going to move the 4 over first. I think that's actually all I'm going to do first. And then I'm going to divide by -4. And if I do that, I would get -x squared plus y squared over 4 minus z squared over 2 equals 1. So the reason this thing is different than the last one is actually just because now there are 2 negative terms. In the last problem, there was only 1 negative term when it was set equal to 1. And this one, there was only 2 that were squared, not all 3. So if you have 1 negative squared term, but the other 2 are positive, you're going to get the nuclear power plant reactor. Then if you have 2 negative squared terms, you're actually going to get this weird shape. And there's something very odd happening kind of in the middle here. And let me try to explain that. So like take, what's an example of one? So if you take y equals 2, all right, y equals 2, if you plug that in, you're going to get -x squared plus 1, right, minus z squared over 2 equals 1. So then the 1s would cancel, and you would get -x squared minus z squared over 2 equals 0. And the reason this is weird is because this equation is impossible. You have, we're really assuming real numbers here, and the only way that this could work is if you had imaginary numbers, and we're not going to complicate it that much right now. But right here, you have a negative number because you would square it and then negate it. So it's a negative number. Square it, negate it, divide by 2. It's going to still be a negative number. So this thing, basically, it's not going to get you to 0. You're going to have a negative number here. And if you go and try to graph this thing, it just doesn't make sense. And just to do another one, maybe, if you do y equals 0, take y equals 0, then you're going to get negative x squared minus z squared over 2 equals 1. And again, negative number, positive number can't be equal. And so actually, if you look at the equation right here a little bit more, the possible values that don't work are really anything between -2 and 2. All of these are bad numbers, and they're basically not in the set of values that will make any sense here. That's why there's this weird gap. It literally is disconnected graph, just the way a hyperbola gets disconnected. This thing is a weird name, and I don't know really where it comes from, but this is called a hyperboloid. And then this part I don't really understand, in 2 sheets. Not so sure where the sheets come in. If anyone wants to find out why we call it 2 sheets, please let me know, because I don't know. But basically, if you think about the equation, when you get 2 negatives, you can get some weird things like this that just don't make sense. And so you end up with like a chunk where there's no output. And that's like the 2 sheets because it's in 2 different parts like that. All right, so I know that was a lot between this and the last video. But these kind of quadratic surfaces are going to show up a lot this year. And you're not going to really be expected to graph them too much, but you do need to know, like, when you look at this, kind of see that really it should have a certain structure, and like it would be the one that's like split like that. And if you see, 3 terms squared, 3 different variables squared, but only one is negative, then you're going to get that kind of hyperbolic, either ellipsoid. It can also be a circle too. If these were, if like these were the same value here, then it would be circular, hyperbolic, but with a circular top, right? So it's really more just a way to make sure that you kind of see some similarities here with conic sections that you learn in like Algebra 2.